Thank you, Professor Hasegawa. It's a pleasure for me to be here at ICRA. Today I'll be sharing with you a sub-area of medical robotics, which you call as rehabilitation robotics. And the goal here is to use robots to help improve everyday functions. I have a series of papers that I'm going to sort of talk about in my talk here, and you're welcome to download this through the QR code. So if you think about everyday human functions, we stand, we sit, we reach for objects, we turn our head, we walk, we climb stairs, and this is something that you do many times in a day, right? We don't even think about how we're doing it. And if you go behind the scenes, right, it's the central nervous system and the peripheral nervous system that coordinates these motions with the musculoskeletal system, with feedback from the sensory systems using visual, vestibular, and proprioceptive feedback. And if you think of the spinal cord, that is a conduit between the motor outputs to the muscles and the sensory inputs going to the brain. And many of the movements and some of the impairments can be related back to this picture. So imagine somebody who has a stroke, or somebody with a spinal cord injury, or a cerebral palsy, or just old age. These simple tasks become a challenge for them, right? And there is really no pill that you can take and improve your function, right? There is a lot of hard practice which goes on between the physical therapists, right, and the clinicians and the patients. Now, the scientific framework behind this is neural plasticity, right? It is the ability of the nervous system, okay, to reorganize itself both in function, right, and with practice. Now, when we do these motor practice, there are a lot of motor training principles that we often use, such as progression towards the normal activity. Okay, a lot of repetition, right? And that's where kind of comes hard work. A lot of challenge and motivation for the individual who's undergoing through it. And also, there's a specificity of the task, right? So when you're training somebody to walk better, you have to make sure that all of that emphasis is around that function. So today, I'm going to talk about a few everyday functions, such as walking, posture and balance, right? Some of the neck control issues, and cognitive health. So the goal of our laboratory, the RO laboratory, is to retrain the nervous system using robotics. And the way we conceive robotics as something that you wear externally on the human body with sensors and actuators, right? And the actuators sort of respond to not only sensors that are collected by the robot, but also some of the physiological data that you take from the human body as well. So here I have a few functions with robots that we use in our laboratory. But I want to sort of refer to a picture in the center, which says training wheels, right? And it's kind of a very important paradigm that we have to remember. Okay, when children are learning to bike, what the parents do, they put a training wheel, a third wheel. And the purpose of the third wheel is to help the child learn to balance, right? Because they are not very skillful in the beginning, right? And the child sort of practices that kind of over a few months, and they become skillful at it, right? And then they don't need the training wheels. And we think about the rehab robotics as training wheels on the bicycle, right? These are machines or wearable systems that you use to train the nervous system, and you're not going to use them later on. Now, there are certain conditions which are called neurodegenerative conditions. For example, ALS or our old age. We can also reverse the cycle. Okay, and in that case, the function of therapy is to maintain the function. Okay, and so what our lab does is to look at all of these different functions and create technologies around them and see how we can implement these technologies to improve human functions. And we also sort of look at clinical data, right? So we bring in patients in our laboratory to make sure that whatever we're suggesting actually translates onto the humans. So you may be wondering why robotics? Right? And if you think of robots, they're really a collection of sensors and actuators, right? And what these sensors do is provide you with objective data, right? And of course, you have a lot of clinicians who are experts in the field, but they have a lot of subjective data, right? And what the robots do is actually provide you objective data to sort of inform them better. Now, also, if you think about the human movement, there are many degrees of freedom in the human, right? If you think of your arm or your leg or your body, there's so many degrees of freedom, right? Think of a therapist working with you. He's got only 2 hands, right? He can only sort of position, let's say, hand on your shoulder and kind of move your elbow and so forth. So what the robotics does, it provides you extra pair of hands, which is necessary for this clinical practice. Now, as researchers and clinicians, we can ask some basic science questions. What if I did this way to the nervous system? Of course, there are well-established procedures, right? But they may not be the optimal or the best, considering that we know so much more about technologies that we can put around the human body. So the way I've divided my talk is in 4 parts. Okay, we look at walking. Okay, then we're looking at sitting posture. Okay, and then we head control, and later on cognitive health. Okay, and within the walking context, we look at stroke, cerebral palsy, and Parkinson's disease. So this is something that fascinated me about 15 or 20 years ago, right? And we asked this very basic question. It's a neuroscience question, right? Every one of us walks, right? Walking is somehow sort of ingrained in our brain, right? We always walk, and you're not even thinking about it. You're texting, you're talking, and you're doing so many different things, right? And we are able to coordinate those movements, right? And if you think about the walking, it's a repetitive cycle. If I think of a coordinate frame at the pelvis, right, it is a continuous motion where you pull your foot backwards, bend your knee, and come forward. And this is a repetitive cycle that you see out here, right? And this is what you see in the video of an individual who's walking with the device, and the robot is just a sensor in this case. So we asked this question, can we actually change the gait of the individual, right? So something that is so ingrained in our brain, can we change through an hour-long activity with the robot? Right? And that's where we created this exoskeleton called ALEX, or active leg exoskeleton. And the idea is very simple. What this robot does is looks at your foot and tries to apply forces on the foot, just like a therapist would do, so that you can learn the path. Right? And what you see here is a template of a path. Right? And this is what I want the individual to learn. Right? And this template could be different from what you're used to doing. Right? And the robot, the way it interacts is with a force field or a tunnel-like force field, and it is an assist-as-needed kind of strategy. If you go too far out of the tunnel, the robot pushes you back, right? And you move it along trajectory. So we have individuals practice for about 45 minutes or so, or an hour, right, with different force field interaction with the foot, right? And in this case, we're going to look at the videos again. This is the motion of the individual before training, right? And this is the motion of the individual after training. In both cases, the robot is just a sensor, right? And you can see a distinct difference in the gait of the individual. The video down is kind of a longer gait and a shallower gait, right? And of course, when we do human studies, we don't do with a single subject. We look at groups of individuals. And that's where we recruited 3 groups of individuals. The first group was given visual guidance. That means you see on a screen the trajectory of your foot and the temporal trajectory. The second one was a force field, which is provided by the robot, and that's where we robotics sort of come in to train the individual. And the third one was force field and the visual guidance together. Each individual was given about 60 minutes of training with the robot with these force fields that I talked about, and we wanted to know about learning and retention, right? So there are 2 aspects of it. Now what you see here are 3 plots. The black plot, which is kind of 100 means that you have actually learned the new template, right? So 0 means you have not learned it all. Okay, and you see 3 time points: immediately after training, 10 minutes post-training, and 2 hours post-training. So, okay, so we want to know how well you learn and how well you retain. If you look at this plot with the black here, you see that the individuals learned the template, and they also retained 2 hours later on, right? But on the other hand, the group which was only given visual feedback, they learned quickly, but they lost it at 2 hours. Right? And the group with the force field was somewhere intermediate in between. Now, this sort of raises some interesting questions, right? I mean, even though we are talking in the context of a walking, but there are many daily activities that we do, right? I mean, think of somebody in the industry who's doing a repetitive motion, loading something, assembling a car, right? There's a whole series of kind of pattern movement, right? Or think of athletes, right, who want to do these great maneuvers and so forth, right? And what it sort of tells us is that these exoskeletons can train the brain to make these movements more correctly. In fact, you can ask the question, right? I'm not a good golf player. Can I become a better golf player? Can I train somebody with an exoskeleton to become a better athlete? So moving on, of course, we are interested in impairment, and one of the things that we looked earlier on was to train the gait of stroke patients. So I'm going to give you a little bit of context within stroke. There are about 7 million people in the United States who are stroke survivors. Just to give you an idea, there are about 350 million people in the United States. About 2% of the population are living with stroke or survivors of stroke. Now, if I look at the template of the stroke patient, okay, he has got a weak side. Okay, often these individuals have something called hemiparesis, right? Their foot on the weak foot would typically have a drop. They drag their toes. They will circumvent their hips. And this is the typical motion that you see. So our goal was, can we actually take the current template of these individuals, right, and expand it, right, because they have a shorter stride length, kind of shorter hip height. Okay, and the way the machine interacted with the individual was exactly the same as what you saw in Alex, right? We created this machine called Alex 2, and that machine allowed us to do a little bit more normal movement and so forth, right? Each of these patients got trained for about 15 training sessions over a 3-month window, right? So think about just a single patient data, right? We had to track them for 3 months. And then we send them home and brought them up 6 months later on, right? So a single patient took us about a year just to collect one data point. What you see here is the group data of the multiple subjects who were involved in it, right? And this evaluation is not done on the robot, but it's done over ground walking. And what you see here on the y-axis is the average ground walking speed, over ground walking speed, right? And before training, the yellow bar basically tells us about 0.65 meter per second, which is about half the walking speed of you and I when we walk in our daily life. So right after the training, you saw a modest increase in the overall walking speed. Okay, but what is very interesting here, that when we brought these patients 6 months later on, right, and did the same evaluation, they continue to improve, right? And that is sort of that is very consistent with the stroke literature, because once you have created a change in the nervous system, you are able to sort of benefit that. Now, over time, we created other exoskeletons. There was the Alex 3, which was a bilateral exoskeleton, and it was really an exoskeleton designed for scientific studies, right? Different kind of force fields, assist as needed, or repulsive forces, or damping force fields, right? Different kinds of human interfaces could be auditory feedback, visual feedback, haptic feedback, combination of these, right? And also the degrees of freedom in the exoskeleton, right? Because you can really design an exoskeleton to do with any number of degrees of freedom. And there are a whole series of published studies that sort of were done with these series of exoskeletons. Now, what we realize that there are many challenges, right? These designs are not ecological, right? What do I mean by that? The weight of the exoskeleton was about 1/3, roughly, of the weight of the individual, right? So 60 kilograms, my exoskeleton weighs about 20 kilograms. Also, exoskeletons have a typical issue of joint misalignment, right? Because the robot that you design has fixed axes. But the human joints are never fixed, right? Because these are bones that are sort of moving relative to each other, so their axes keep on changing. So there's always going to be misalignment between the human joints and the machine joints. Also, one of our goals is to sort of take these ideas to the community, right? So, of course, we want to do the scientific work in the laboratory, but we want to take it out to the community. So these drove us for the different research questions that we worked for the last 15 years while I've been at Columbia. And one of the first innovations that we did is we created this design of cable-driven exoskeletons, right? And in fact, this was the first design in the literature, which was a wearable design, right? In fact, we first designed an arm exoskeleton called Carex, right? And then later on, we created this Alex device, which is the C-Alex device, right? And our arm exoskeleton got the Best Student Paper Award in ICRA about 2012. That's about maybe 12 years ago, yeah? And we were able to show that with this exoskeletons, we can actually achieve the same kinds of human interfaces to train the nervous system, right? And there are a series of published papers that we did on healthy subjects as well as stroke survivors. Now, as you probably know, that this cable-driven exoskeleton has become a thriving field in the area of rehab robotics. And I'm very proud that this is something that our colleagues are taking it further. So another interesting idea that we asked ourselves is, can we design non-exoskeleton type, non-exoskeletal designs for human movement training, right? And some of this is motivated by the picture that you see of the mother and the child, right? The child is learning to walk, right? And what is the mother doing? Kind of supporting the child in the pelvis, right? She's not actually using an exoskeleton to sort of move your leg in a repetitive pattern, right? And believe me, all of us have learned to walk, right? Now, if you think about what's happening out here, what the mother is doing is providing an assist-as-needed strategy, right, to help the child to learn. And you allow the child to make mistakes, kind of let them fall down, right, and eventually learn and so forth. So what we want to do is use this idea to create an exoskeleton, which is, we call it T-pad, or the tethered pelvic assist device. So it's a small pelvic belt connected by wires, right? And you can connect as many wires as you want to, and with these wires, you can create forces and wrenches on the human body. Also, there's a camera system that is integrated into it because you need to sort of do a tension decomposition along the wires to get an external force and moment onto it. Now, as you know, that cable-driven systems are unilateral in nature. You can only pull a cable but not push a cable, right? So most of our designs are N+1 designs, and those of you who are familiar, it's not the 2N degree of freedom design, but it's an N+1 design. Now, with this device, we can really kind of do a lot of kind of interesting research. So, for example, we can apply continuous forces, we can apply intermittent forces, we can provide little force pulses, we can synchronize with the gait, and so we can really tweak the nervous system and see how the nervous system responds to it. So, I'm going to show you the first experiment. This is to look at children with cerebral palsy who have a crouch, right? And you can see the child walking. He's walking with a crouch. He's got knees are bent, your hips are bent, right? And it turns out to be that there are about 500 children in the United States who have cerebral palsy. And about 2 to 3 out of 1,000 live births, children are diagnosed with the cerebral palsy. Now, some of these children walk with a crouch, right? And you saw bent hips, knees, abnormal joint load. Very soon they will be on wheelchairs, right? And also when they walk, they are not walking with a heel and toe, just like you and I walk, right? They have a flat foot, or they may have a toe landing, and so forth. Okay? The typical way of rehabbing these individuals is something called a body weight suspension. So you have them walk on a treadmill, you apply a certain percent of body weight, and make them easier to walk because you have taken a part of their body weight, right? And they walk well on the treadmill, but when you put them down on the ground, they're kind of still crouching. So we said, how about we do something different, right? Instead of doing a body weight suspension, why not do a body weight augmentation? So this is when we said, we're going to train these children over multiple sessions, but we'll apply a 10% body weight through our cables as they're walking. Okay, and according to the motor learning principle, we would use the speed of the treadmill as a way to progress and challenge the individual. Okay, so this is the video of a child, okay, kind of some of the early training, kind of later training. There were 15 sessions of training, right, over a 3-month period, right? And what you can see here in the video, the child in a later training session, they are walking with a longer step length, right, faster and so forth. Also, if I look at the ground reaction force that we can take from our treadmill, you can see that in the beginning of the training, they didn't have those peaks that I talked about. But by the end of training, they had developed those peaks. So let us see how these children walk, right, over ground. Because really the proof of the pudding is not how they walk on the treadmill, but how they walk over ground. And you can see in the video that same child who had a crouch is walking much more straight. And I encourage you to kind of look at this paper. There's a lot of detail. There were 5 children involved into it with a post follow-up. So let's kind of move on to another application, right? Balance is very important, right? I am from New York City. Kind of we travel by subway trains. The trains shake around, right? And you have to catch yourself and balance yourself, right? And you can think of this as a way as a therapy. Right? What we did is we used this T-pad device to simulate, okay, balance perturbation in the laboratory. And we can sort of provide these perturbation pulses, okay, in any direction, right, randomly. And we can have a large pulse, small pulse, and so forth. And we look at how the human neuromuscular system uses to regulate that. So we have done a number of studies with the T-pad, including young people, very old people, people with stroke, people with cerebellar ataxia. But I'm going to show you something here with Parkinson's disease, right? Just to put a context, there are about 1 million people in the United States, according to Michael J. Fox Foundation, who are with Parkinson's disease, right? And our intervention was about an hour, right, with randomized forces in different directions. Right? And we look at how that...
It looks a little like Harry Greenwald is getting ready to go skydiving, or maybe bungee jumping. But this is actually part of a study to prevent potentially serious falls. Very important because Harry has Parkinson's.
There have been times when I could feel my forward foot not quite grasping the next tread on the stairs, and there are times when we're walking down the sidewalk I have to remind myself, for posture issues, I should be raising my head and looking ahead because Parkinson's has got me looking down a lot.
40% of people over age 65 suffer a fall at least once a year. That number is much higher for people with Parkinson's because the disease affects their gait and balance. So Dr. Sunil Agrawal at Columbia University has devised a system to teach Parkinson's patients how to keep from falling by training them to recover when this elaborate contraption tries to disrupt their sense of balance.
We give them the experience of being able to recover better from this momentary loss of balance and be able to train their neuromuscular system to be able to be more responsive when a fall appears.
In fact, Dr. Agrawal's study showed that just one training session substantially improved Parkinson's patients' balance and ability to avoid falls. The harness prevents Harry and others from actually falling, of course, and the better they get, the stronger the jolts come, and from different directions. Although Harry had to learn to trust the device.
I relaxed a little and said, okay, I'm not really going to hit the ground here. Hey, it works. The harness really is going to keep me up.
Now, Harry says he's more confident now walking and especially going up and down stairs. The balance disruption system is just at Columbia for now, but it could be rolled out to other medical centers. You only have to prevent a couple of serious falls in Parkinson's patients to make it all cost-effective. It looks a little like...
So our goal is not only to sort of build these technologies for the laboratory, but this is to translate this idea to the community. And that's where we created a device called mobile T-pad. And we use a commercial rollator, and we put motors and the control system on top of it. Now, there were a lot of interesting engineering challenges of how to implement this, because we do not want to use a motion capture system in this context. And the way we got around to this is creating a connection through the cables in a way that you can do the forward kinematics in real time. And there are many published papers to kind of show the validity of this algorithm in terms of its accuracy and so forth. Now, I'm going to share with you one of the recent studies that we did. We just published in Bioengineering. These are stroke patients. We saw that many of these patients have hemiparesis, right? And what this really means is that they walk with a limp, right? So each time their weak foot comes on the ground, right, they're not very confident on that, right? And so they want to hobble and get onto the other one, right? And so that's why you have got to time asymmetry of the gait. And in order to sort of rehab them, what we need to do is have them bear more weight on that weak leg, right? And what the robot really does is pulls the center of mass on the weak side each time we know that that foot is going to be on the ground. So here's a video of a stroke patient sort of walking with the device in the laboratory, right? And on the right, this is a 4% body weight lateral force that we are applying so that each time the person is able to puts his weak leg. Now, what we were able to show is through these kinds of training, you can actually make them more symmetric, right? Because now they're able to generate more force from the weak leg, right? And they're able to be more symmetric. So I would encourage you to kind of read the paper for more details. So let's kind of move on to the next segment, which is posture and the human core, right? And we know that core is very important, regardless of whatever you do, right? Whether we are kind of moving our trunk, reaching out for things, right? And if you think of the pelvis, right, that connects the lower body and the upper body, right? And the upper body is the core. So we're going to talk about in the context of children with cerebral palsy, spinal cord injured patients, and also just old age. And I'm sure that you'll relate this problem to this system. So what this device is, again, a belt, right, with these wires, right? And what we're looking for here is to improve our trunk control, right? So in order to sort of get an appreciation of this, as you are sitting and reading and you're hearing me, just extend your arm, right, while your foot is in the ground, and see that there is a certain workspace that your trunk can move before you can do that any further, right? And if you do this around 8 directions around you, what you get is a certain envelope, right? And this envelope is kind of shown out here with this red polygonal shape, right? And everybody has this had the shape, right? Some larger, some smaller, right? Some asymmetric, right? Some people have a better balance in the forward direction, not enough sideways. And the goal is to expand this, right? Regardless of whether we are young people, we are healthy people, or people with impairments, right? And also sort of make it symmetric all over. So what is the role of robotics, right? So what the robotics does, it interacts with the human body in a different way, right? What it does is creates a little donut-like force field, right? And each time you hit the wall of the donut, right, it applies a force onto it, or gives some assistance if as needed, right? And the control parameters is where you place the donut, how much force you do, right? What is the radius of the donut, and so forth. So we're going to show you what we can do with this technology. So here are some children in our laboratory. This is a child with cerebral palsy. He's a GMFCS 3 or 4, right? Which basically means that he doesn't have a good trunk control. And the goal is to, and there's a therapist who's interacting with the child in our laboratory. And what she's really doing is using the ball as a way to know how far he can reach, or trunk center can reach in the forward direction. And if you do this over the 8 directions, you get this polygonal shape here, right? And it gives you a boundary of the workspace. And the goal is to sort of expand this boundary, right, and make it circular and so forth. So how do I do this? So here is a child interacting with the device. He's a physical therapist who's kind of doing the training, okay, in these 12 sessions, right? Each of the sessions is about 90 minutes or so, right? And what he's really doing is using this boundary-based control, right, and mixing it up with fun games, right, to keep the children interested. So we're going to see a child, right, before training and after 12 sessions of training, right? You look at the video on the left, how much the child can move relative to the vertical, about maybe 15, 20 degrees. While if you look at the video on the right, the child is able to go almost all the way up to like 70 degrees and come back to the neutral, right? And that is our goal, is to be able to expand that envelope for the child and improve the core of these individuals. So here is some data from 3 children, and this is the published data. There are 12 training sessions out here. That's numbered 0, 1 to 12. Post-training and a 3-month follow-up. On the y-axis is a measure, which is the workspace boundary, the workspace that you saw. And what you see here is through training, right, every training we are kind of linearly kind of improving that workspace, right? And some of that is lost so after 3 months of training. But what's important here is, I mean, we can have so many different outcome measures, right? And one of the big outcome measures is the quality of life of these individuals, yeah? And right now we have an NIH-funded project. This is an R01 clinical trial where we're bringing in 85 children with cerebral palsy. We'll randomize them into 2 groups, and one of the groups will get this robotic trust training, while the other one with the conventional one, to see what's the difference in terms of their outcome. So we are recruiting children from all over the country. There's a child who...
We came from Florida, so it was a long way. Everyone here is so kind, made her feel so at home.
I liked all the games.
She plays a lot more with you guys, doesn't she?
She can throw balls better.
If she's eating, she will be able to stand up on her own and then reach over the table and grab some stuff. And she used to not do that at all. And she does her hair in the mornings now.
Yeah. And these are amazing, right? I mean, simple things in our daily life that we can do, right? But if some of this training enables us to do that, there's a huge impact that we can put on society. So we did something similar for spinal cord injured patients, right? And just to give you a context, there are about 300,000 patients with spinal cord injury. This is a lesion on the spinal cord, right? And so there is depending on, there's no communication between the brain and the spinal cord below the lesion. So many of these individuals are on a wheelchair. So this is an individual who we brought in. he works in a local Walmart store, right? He had this injury about 23 years ago, right? And what we're really doing is we are trying to expand his workspace, because as somebody who's sitting on this wheelchair, there's a big necessity for him to be able to access kind of area around him. Now, this is something that we were doing just before COVID. So we had to stop the session. We had only 6 sessions of training, but there's a case study that is out there, and you're very welcome to read through it. But some of the important sort of conclusions were that in just 6 sessions of training, we were able to increase the workspace of this individual by 400%, right? There is a clinical test called T-shirt test. It says, how much time does it take you to wear a T-shirt and take off a T-shirt, right? And you can think about why that is an important clinical test, right? And what we were able to show that we could halve the time of taking the T-shirt on and off with this therapy. So now you can relate this, okay, to many individuals in our society who are elderly, right, who are sedentary, right, and many of them can benefit with this kind of technology. Now, another moonshot project for us is how do we get spinal cord injured patients to walk, right? And of course, you have to stand first before you can walk, right? And one of the enabling technologies is called spinal cord epidural stimulators, right? So these are surgically implemented patches in the spinal cord, and you can electrically stimulate this cord. And what has been shown is that you have a larger muscle activity because of this stimulation. However, from a functional training point of view, you still need to integrate those signals, right? Or coordinate these signals in order to do the functional activity. Now, this is a picture from one of our collaborators. Her name is Susan Harkima at University of Louisville, right? And this is a patient with this stimulator on, right? And there are 3 therapists around this individual. The person at the back is basically providing sensory perturbation to the individual, while the people in the front, they are just kind of providing support in case the person falls down, because the person with the spinal cord injury, he doesn't have the ability to control himself. Now, what I want you to sort of notice is a handlebar, right? And just think about this question, is this ecological, right? When you are here in this audience, right, and you have an internal or external perturbation, you don't have a handlebar, right? You use the muscle signals within the body to sort of regulate yourself, right? And that's where we thought about this new device. We call it Robotic Upright Stand Trainer, which is an acronym for ROBUST, right? It's again 2 bells, one at the pelvis, other one at the trunk. Right? And you have many of these cables that allowing you to sort of perturb or kind of hold you. And this is an instrumented device. You have force plates, you have a camera system, you can do EMGs, you can do lots of neurological signals as well. So we installed this device at University of Louisville about 5 years ago, and we have 5 patients with ASIA A and B. These are the most severely injured spinal cord patients. And we had 80 sessions of training with them, with this device, right? And what we were able to show, and these results are just being published in the neurotrauma journals, and what you can show is that these individuals can stand upright and also make self-initiated movement. Now, we have another 5-year grant for this same idea, and now we are partnering with Kessler Rehab Institute in New Jersey. They're about 18 miles from New York City, and they are a #1 hospital for spinal cord injury rehab. And we'll be very excited to report back later on about this. Now, as you can see here, there are lots of new technologies that are coming together here, and we have seen a lot of these here in the conference. Virtual reality, augmented reality, right? Machine learning, right? And the question is, how do we sort of harness all of these things within the rehab community? Right? And one of the questions that often people think that using an AR, VR is better, right? But there's no convincing data or results to kind of show that. So we asked the question, if I take a group of healthy individuals and have them do these interventions in 3 cases. One is the physical reality, that's what you saw in the top video. The second one is virtual reality or augmented reality. And we want to see what kind of performance gains are there. And what we found is that the group that uses the VR or the AR actually improve their function a lot better than the group that doesn't, right? We also kind of measure a lot of the psychological factors, right? Engagement, right? Kind of immersion, right? Sickness, and so forth. And what we found is that with the AR was actually a little bit better than the VR. Now, another thing that you saw in my video here is that when a therapist is interacting with the child, right, there's a lot of cognitive demand onto it, right? Because the therapist doesn't really know in what direction the child is going to move or how far he's going to move, right? And what we're doing is we are using the real-time data, right, like a 50-millisecond data, to predict using a deep learning algorithm as to where the child would go, and that could sort of be used as an aid to the therapist. So I think there is a great opportunity to integrate some of these technologies as we go on in the near future within the rehab robotics community. So let's kind of move on to the third segment, which is the neck control, right? And we know that neck is very important, right? Or the head is very important. It kind of has all of our sensory signals on it, right? I mean, eyes, your vestibule, right? Or your proprioceptors. I mean, on the neck, they're all there. So that means if you don't have a good control on your head, right, that sort of affects everything in terms of your movements. Now, this particular project was really motivated from ALS, right? And some of you are probably familiar with this. These are slow kind of death of alpha motor neurons, which control some of the muscles in your body. And probably some of you recognize the figure here on the center. Now, we have used this, so we were the first group to actually create a robotic neck brace, right, which is kind of uses the human data, right, and now it's a 3 degree of freedom exoskeleton-like device that you can put on the head with respect to the shoulder. It's a parallel actuated 3 degrees of freedom system, and we have actually used this for over 500 people in different studies in our laboratory. What you're seeing here in the video is a patient with ALS, right, who cannot sort of control their head-neck movement. And as you can see, it's kind of so important. When I'm talking with you, I'm moving my head, neck, right? I'm moving my eyes, right? And that's an important part of any social communication, which is currently not being studied by our rehab community. Now, also, we are expanding the use of the neck braces. So we have a new study that is funded through the NIH to looking at how do you improve the neck control in patients with cerebral palsy. Another study that we are doing is looking at elderly individuals with degenerative disc diseases, right? So a lot of us have these neck pain as we grow older. And one of the conventional kind of treatment methods is something called traction forces, right? And these are typically delivered by the therapist as you're lying down on a bed, right? And so now we have created these devices that are sort of uniquely applicable to these. And while you're wearing this device, you can actually create these controlled traction forces through here. So some of the first papers on this are just about to get published in the literature. Now, as I said here, the head neck is very important, right? And just to kind of put a context out here, there are about 70 million people in the United States, right? Just to kind of give you, it's a huge number. It's 1/5 of the population of the United States. They have got these vestibular deficits, right? So people have vertigo, right? They are not able to kind of discriminate, right? Also, as we grow older, our visual system and the vestibular system decays over time. Also, what the brain does, it integrates these signals, right? And from that, I mean, it's uses a SLAM-like algorithm to know where I am. Right? And if you cannot do that well, right, you would not be able to take the right action. So what we're really doing is creating portable systems, and we actually, some of this data was actually obtained in a community, in an elderly center community in Delaware. And we are integrating virtual reality and our head neck brace to provide these sensory dither into the system. Right? And in this case, we can do visual perturbation, we can do vestibular perturbation, and see how that affects gait and balance of these individuals. Right? And some of our studies that were just published, we can actually show that these individuals have higher gait variability and balance variability, right, when you perturb these sensory conditions. And these can be used as a screen for older adults who may be at risk for some of these issues. Now, another thing that we all know, as we grow older, your cognition, your memory, and task execution gets affected. There are about 15 million people in the United States who are diagnosed with mild cognitive impairment, right? And about 1/3 of those have something called Alzheimer, right? And these are called dementia, which is due to Alzheimer. Often you need screening tools to know if you can sort of know ahead of time if somebody has kind of progressing into these conditions. Now, one of the tests that has been used is called floor maze test, right? So what you do is you draw a floor, your maze on the floor, right? You show the maze to the individual, and then you ask them to negotiate the maze or complete the maze. And it turns out to be your performance in the maze is very well correlated to your cognitive score or your executive functioning score. So what we really did is created a virtual reality version of it, right? Where we can actually change the complexity of the maze, right? Also, you can sort of really change the different conditions of the maze. So what I'm showing you here is a video of two conditions of the maze where we actually raise the walls, right? So in one case, you have the view of the entire area, right? In the other one, you are kind of a blind alley, and you can't see your next alley. And we have been able to show through a lot of data that these maze and performance in the maze, the gait, balance, some of these measures are very correlated with cognitive impairments and older individuals and their performance. So we know that as we grow older, right, there are many facets, right, in which our system sort of decays, right? From a balance perspective, right, you heard that about 40% of the people who are 65 years or older, they fall once a year, okay? Believe me, it's true. I have had my fall, right? I had to go to the ER for that, right? And so we need technologies not only to look at mobility, but also look at cognition, right? How do you sort of create technologies that are not only good for your gait and balance, but also improves your cognitive ability? Because sharpness of the mind is as important as able to execute your movements. So this is a study that we recently published. This uses our mobile T-pad, and we recruited a group of 40 individuals from our community, right? And we had two groups. One group was given this perturbation as they were walking, right? And the other group was not. And what we found is that through this particular training, you could actually improve their gait, balance, and cognition, right? And so these are some of the first evidences that your circuitries in the brain that are around cognition are also sort of linked to the balance and the gait. So I'm sure that there'll be a lot more of this in our community as we go through some of this. So what have I sort of, let me kind of summarize some of these things. Okay, I showed you 4 functional tasks: walking, posture and sitting, neck control, okay, cognitive health, okay? And I think there's a huge societal impact that we as a community can make on people, right? So if you think about the World Health Organization and the GATE initiative, it says that there's 1 billion people in the world who need assistive technology, right? Kind of these numbers are mind-boggling, right? We don't even try to think about this. Now, the elderly population in the United States will double in the next 25 years. This is just the statistics from the United States, right? But there are similar statistics in all around the world, right? If you think about Japan or Korea, they're already out there, okay? Now, some of the impairment demography, I can talk about stroke, cerebral palsy, spinal cord injury, right, ALS. And if you look at in terms of percentages, right, they are similar all around the world, right? I have some collaborators in Uganda who work with cerebral palsy. Okay, in the United States, there are about 2 to 3 children per 1,000 who are born with cerebral palsy. In Uganda, it's 4 to 5 per 1,000, right? But the numbers are not drastically different. Anything that we are suggesting out here can actually be implemented, right? And we, as rehab roboticists, should kind of make an effort that all the technologies that we bring out here can actually impact people in their lives. Now, what you also saw is the small changes in function, okay, improves quality of life in a big way, right? So these outcome measures that we have, even though they may kind of be very restrictive, they may be very granular, but they can actually impact people in different ways. So what are some of the key takeaways from my talk? Of course, I think the rehabilitation systems, I mean, if I remember, the first conference in rehab robotics was in 1994, and that in Wilmington, Delaware, right? And I used to be a professor at University of Delaware at that time, right? So this field is not long. Not very old, right? It's only about 30 years or so. When we make these rehab systems, they should be ecologically valid, right? I see a lot of engineers building exoskeletons, right? But what's the purpose? What are you trying to sort of achieve with these exoskeletons? And that is very important, right? Because that sort of kind of sets the trend of what your outcome would be later on. You should target specific users, right? So a person with cerebral palsy is different from somebody with stroke or with somebody with Parkinson's disease. You have to know the etiology. You have to know the people and the limitation and what they need. Also, you have to go to the functional need, right? What specific functional need you're addressing? Now, some of the interface and training, they have to embed these neurophysiological principles. I talk about the motor learning principles. They're very important to embed in the design, right? Otherwise, you're not going to see the clinical result that you're expecting. Now, as a group, we have to demonstrate the scientific feasibility of these ideas, right? And pre-post evaluations of this technology is very important, right? And if you are targeting a stroke patient or a certain group of individuals, you have to sort of go to those community and do these tests and make sure that your outcomes sort of measure up to what you're expecting. Now, multi-session training, right? What you saw in my talk here, many multi-session training. A single stroke patient to get data, we had to work with that patient for nearly a year. It's amazing kind of life-changing experience, right? Many of you know that I used to work in differential flatness before, right? And I sort of, about 20 years ago, I kind of took a turn, right? Because it was so heartwarming to see how your technology can improve people and their lives. What is my vision for the future? We want to bring robotics to the home and community, right? To us, right? At the end of the day, we all have to ask the question, what are we doing and why are we doing those, right? And we are all there to make an impact, right? What can be a better impact to sort of improve the functional ability of your loved ones, your community? So, well, it takes a village to raise a child, and I was no exception. I want to thank my graduate advisors, Professor Bernard Roth, Professor Ken Waldron, Professor Khatib. I had many clinical collaborators over the last 25 years or so. Notably, Professor John Scholz and Cole Galloway at the University of Delaware. So I used to be at University of Delaware for about 15 years before I moved to Columbia. Professor Joel Stein, who's the physiatry-in-chief at Columbia Rehab, as well as Cornell Rehab. Professor Hik-Young Kim, he's a pediatric physiatrist who I work with a lot of cerebral palsy children. She's now a chief physiatrist at UT Southwestern in Dallas. Professor Susan Harkema, who's at University of Louisville. Also, I want to acknowledge a lot of my graduate colleagues and mentors. I mean, we all go for lunch, right? We have kind of play tennis in the evening, but these are also great experiences because they are kind of lifelong bond that you make with your friends. Notably, Professor Vijay Kumar, Professor Joel Burdick. I know that Joel is here in the audience somewhere. Professor Ron Fearing. These were all colleagues at Stanford when I was a student. I was very happy to get feedback on this talk from Professor Mark Katkowski. I saw him in the audience. Professor Connor Walsh, Professor Scott Delp. Also, a whole series of students. I've had about 40 plus PhD students who graduated from a laboratory. I've learned something from each one of them. Some of my students are here in the audience. I've had a lot of postdocs, a lot of visitors. And that has sort of really kind of helped us to bring this in a very diverse way. I was fortunate to start a journal called Wearable Technologies. We are in the 5th year. I have an incredible editorial board. We just got a site score, which is about 5.7. We should have an impact factor soon. Last but not the least, I want to thank my family for supporting me over the years. My wife is here with me, Seema. I'm really thankful. So before I end my talk, I want to just let a few videos play. These are things that are from our laboratory. I'll let you kind of see these. I didn't get a chance to talk about these, but these are self-explanatory, and I hope you enjoy it. So thank you. Arigato gozaimasu, and I'm happy to take any questions.